So now that we've got adding and subtracting under our belts, let's take a look at multiplying. Okay, so multiplying, we're going to compare it with what we know about multiplying already, and then we're going to go into something else that's a little bit more specific to vectors, okay, linear combinations and whatnot. So, but we'll start off with multiplying. So as a recall, remember multiplication can be expressed as repeated addition. So we start with adding. We add vectors together and see if our definition for multiplication of scalars works the same way as it would for vectors. So adding vectors, repeated over and over, can we say that that's like multiplying a scalar quantity times a vector? What does that mean? And to help us demonstrate that, we take a look at this investigation here. What I'd like you to do is I'd like you to pause the video or pause the recording and go through these six and understand what we mean by when we take a look at, for example, what would 2a or 2 times vector a look like, 5 times vector a, and then when we say, well, let's multiply the vector with a -1 or a -3. Understand that concept first, okay, and then go ahead and restart the video. So let's go through a quick summary of what you just went through, hopefully. All right, so scalar multiplication. What is scalar multiplication? Okay, we're going to be taking a look at probably 3 different types of multiplication with vectors. This is just the first one. All right, so scalar multiplication. If we have a vector v and a scalar k, then k times vector v is a vector such that k vector v is, now we have the absolute value of k, all right, so we just take a look at it regardless of what k is, negative, positive, or 0, all right, it's going to be the absolute value of k times the length of vector v, all right, so if k is a positive number, then k times vector v is k times the length of vector v, and it's in the same direction as vector v. If k is negative, all right, then kv is in the opposite direction of vector v, but again, it's the absolute value of k times vector v, okay, the length of it. And then the easy one is if k is 0, then we're going to end up with the 0 vector. K times vector v is just the 0 vector. Okay, that's the definition of that one there. All right, so hopefully you've got that from that little investigation that you just did. Now, definition, collinear. Collinear just means that you have any 2 vectors that are scalar multiples of each other. A scalar multiple, right? We could have, for example, we had a bunch of scalar multiples in this investigation here because vector u, all right, is 2 times vector a. So u and a are scalar multiples of each other, okay? Also, if you take a look and say vector u and vector v are also scalar multiples of each other because they're scalar multiples of vector a, both of them. Okay, so that's how the scalar multiples work, or collinear. All right, so one and the same thing. So that's just multiplication. All right, now with scalar multiplication, we know that we have the distributive property. All right, you multiply the scalar outside the bracket with the 2 quantities that are inside the brackets. Okay, and that's what we have for the scalar, for the distributive property. We're going to prove that that holds true for vector or over vector addition as well. Okay, so what we do is we take it by the 3 cases. K is 0, K is positive, K is negative. Okay, if K is 0, it's very clear to see that both the left side and the right side will end up being 0 because you're multiplying, you're getting the 0 vector on both sides. Okay, now follow along with the positive case. So if K is positive, what we do is we set up our diagram so that triangle ODC is similar to triangle OBA. Take a look at the diagram that we have. So we're going to assume in this case that K is the scale factor. It could be any positive K value. All right. All right. From basically from OBA multiplying K up to ODC. All right. Two ways to look at what is the vector OD. Well, vector OD, we can say that we are going to travel from O to C, so that's vector OC, and then we're going to go from C up to D, and that is vector CD. Okay, so OC, we can see because we use the scale factor, is K vector A, and CD, using the K factor, the scale factor again, is K vector B. All right, now, the other way we're going to take a look at OD is just simply using the scale factor. We know that OD is simply just K times A, vector A plus vector B. All right, vector OB rather. All right, OB is here, K times the OB. All right, and OB is vector A plus vector B. So we have this in here. So we have two different ways of expressing what vector OD is, and you can see that those two ways put together give us the distributive property. Okay? So what I'd like you to do is, on your own time, take a look at page 33, number 20. Actually, this is from a different handout here. We're not going to worry about that. But what I'd like you to do is take a look proving if K is a negative number. How does your diagram change? How does that relate with similar triangles as well? And then you can see that. All right? Okay. So let's take a look and see if we can express using scalar multiples, collinear vectors, using addition, subtraction, and see if we can come up with what these vectors are. All right, so we look at the rectangle that we have, ABCD. You've got X and Y being the midpoints of vectors AB and AD. You can see that from the diagram. They're illustrated there as well. Vector A is the vector AX, and vector B is the vector AY. All right, so express each vector in terms of vector A and or vector B. So vector AB, you can see, is twice as long as vector A. So in that case, you would get 2 vector A. All right. Go along if you want. You could pause the video, try it yourself. That way you're thinking through these things, and then come back and listen to some of the explanations. So dA, you can say, come through. It's in the opposite direction of vector B, but it's twice as long. So the opposite direction, twice as long as vector B. All right. XY. You can see we start at X. You can write this, and we go to A, which means that we've got a negative A. So that's negative A, and then we travel up vector B. You can write that as negative vector A plus vector B, or you can say it is B minus A. All right. YC, let me erase some of this stuff here. YC, you can read that straight across. You can say that we go up vector B, and then we have 2 vector A, or 2 vector A plus B. XC, we can go A plus 2B, right? A plus 2B. And finally, BD, we're going backwards basically from vector A. So we have negative 2 vector A, and we go up in the same direction as B. So that's plus 2 vector B. So you can either say what we've got written, or 2 vector B minus 2A. All right, so what we've got here is basically what we call linear combinations of these two vectors. We're expressing any vector that's on this rectangle, all right, in terms of these other two vectors, okay? Now, these two vectors are non-collinear, right? They are not scalar multiples of each other, all right? And we're going to use that in order to take a look at what is a linear combination of vectors, okay? To show something specific about two non-zero, non-collinear vectors. All right, so follow along in this one. We're going to start off with, we have two specific vectors and we can place them tail to tail. All right, and that's what we do in this case. Notice that you can move vectors anywhere on, let's say, your tabletop, your sheet of paper, whatever we call it, a plane. All right, and so long as we keep the same direction and the same magnitude, all right, then we can move them and arrange them tail to tail to set up like the diagram that we have. All right. What we're going to do is say that we can express a third vector, and this is vector OP, all right, in terms of the original two, OU and OV. All right. So by looking at the two vectors as far as a linear, parallelogram law, all right, we can arrange our two vectors UV, tail to tail. We have OP is obviously at the same tail. And what we do is we extend our U vector, all right, just enough, exactly enough by a scale factor of S, okay, in this case. And then we take our V vector, and again, we extend it just enough, a scale factor of T, so that we can create this parallelogram so that we hit the head of P, all right? Notice that this works, okay, all the time, and we can end up with our vector itself, OP in this case, okay? So we've got that if the vector itself is at the tail of O, all right? Now, what we're going to do is we're going to take a look and say that our third vector doesn't have to be at the tail of O, okay? It can be anywhere on the plane itself. And that's what we have in this diagram over here. I just want you to see it, to see how we're going to be doing this. The vector itself is DC, okay? DC. Now, here's what we're doing. We've got vector U, vector V, just like we had before. They're two non-collinear vectors, all right? We're going to express any vector DC in terms of U and V, okay, is a linear combination. So again, they're on the same plane, they're on the sheet of paper, they're on your tabletop or whatever, all right? UV are arranged tail to tail, DC isn't, and we're not going to move it down, okay, and be tail to tail. In this case, what we're going to do is this. Follow along here. D is the head of the vector OD. Okay, notice it's OD there. What I'll do is I'll just change the color over here. And here we go. D is at the head of this vector OD. C is at the head of the vector OC. Okay? Now, notice very quickly that there's a linear combination between OD, OC, and DC. Right? DC, vector DC, we can see is OC minus vector OD. This is vector subtraction, right? Now, all we do is we take a look and say, well, OC is set up exactly the same way as this OP was, and it's a scalar multiple of UV. Well, same thing goes with the OC. It's some sort of scalar multiple of UV, right? So we can say, well, it could be a KU plus an LV. That's what the OC is, right? No matter what the scalar is, K and L. OD is the same thing. It's set up right at the tail, the same tail as U and V. So again, we can express it as another scalar multiple of the other two, of U and V. So basically, we just pick any other letters. We can say SU plus the TV, vector V, right? And now, since we have the distributive property, we know vector addition, vector subtraction, and the scalar addition and subtraction, we can basically say that we've got K minus S times vector U, all right? Add that to L minus T vector V, right? Take a look at that, make sure you understand it, because the last part is pretty simple, because basically a scalar minus a scalar is another scalar. We know that whether the numbers are 7 and 4, we get to 3, or anything else, any other combinations, we know it's just another scalar. So we can say, okay, well, that's some scalar A times vector U plus some scalar B times vector V. So we have a linear combination, right? So a third vector that doesn't have the same tail as the other two vectors that we have can always be written as a linear combination. All right, this is an important concept we're going to be using later on in the course as well. It's basically any two non-collinear vectors can span the whole plane. All right, we'll be talking about that. All right, and so you can take a look at the written out proof here as well. It basically says the exact same thing. All right, so what I'd like you to do now, all right, the example here is basically just expressing, you know, these two in terms of any other vector here. And I've given you the example. Okay, well, you pick your two non-collinear vectors U and V, draw out 3 times vector U minus that with 2 times vector V, and that'll get you your W. Draw these out, okay, so you can see it geometrically. All right. Then we've got this, the homework here that you can take a look at. All right, understand those. Again, if you have any questions, let me know in our Teams meetings.